Welcome to the deep dive. Today we're digging into something pretty fundamental, revisiting a question that, well, the pioneers of computing like Turing and von Neumann were asking decades back.
Yeah. What is the real connection, mathematically speaking, between a computer and the human brain?
Exactly, it's a huge question.
And it's driven so much research. But, until quite recently, our best AI, things like the transformer, they seemed, well, totally different from how the brain is built.
Right, you had these dense tensor calculations, all very centralized, getting amazing results.
But then you look at the brain, it's this massive distributed graph, right? Something like 80 billion neurons, all interacting locally, scale-free, uniform. It's just looked completely different, like apples and oranges. Or maybe oil and water is better.
But the research we're looking at today suggests maybe that contrast isn't quite right, maybe it's an illusion.
They're putting forward this new architecture. They call it the Dragon Hatchling, BDH or BDH GPU for the practical version.
And the claim is pretty bold. It's the missing link that finally connects these two worlds. It's not just inspired by the brain.
No. The claim is stronger. It suggests the mechanism we see in modern LLMs, like attention, is actually a biological mechanism, or at least mathematically equivalent.
Okay, so that's our mission for you today. We want to pull out the three key connections this BDH model seems to provide.
Right. First, how does the architecture itself bridge that gap? Second, how does it reinterpret attention, that core reasoning mechanism, in biological terms?
And third, what are the practical upsides? What does this give us right now in terms of building and understanding AI? We're really going for the micro foundations here.
Deep down into how intelligence might actually work.
So let's start with the architecture. The transformer, as we said, it's all about the tensor, this giant centralized block of numbers. How does BDH, the Dragon Hatchling, approach it differently?
Well, it basically throws out that central tensor idea, at least conceptually. It's designed around a network of locally interacting. They call them neuron particles.
Neuron particles.
Yeah. Think of it less like one big computational block and more like a huge forest, high dimensional, where each tree, each neuron, only really talks to its nearest neighbors.
Not broadcasting to the entire forest?
Exactly. No global broadcast, it's all local chatter.
Okay, but my first thought is, that sounds kind of slow on the hardware we actually have. GPUs love big, dense matrix math.
That's the challenge for sure. We'll get to the GPU part, but first, what defines the structure? It's fundamentally about local distributed graph dynamics.
Right.
Intelligence emerges from those tiny local interactions, and it's built using pieces we see in biology. There's an excitatory circuit that amplifies signals and an inhibitory one to kind of tamp down the noise.
Makes sense, like biological neurons.
And critically, they use integrate and fire thresholds. A neuron only sends a signal if its input crosses a certain level, like a real spike.
That really is a different perspective, isn't it? Designing for local rules. The researchers talk about axiomatic AI. The idea being, if you understand the absolute basic rules, the micro foundations, maybe you can actually predict what the whole system will do long term. Mathematically.
That's the dream. Understand the local, predict the global. If you want to get a handle on emergent complexity, you have to start small, locally.
Okay, but back to my hardware question. This elegant graph theory is great, but if it crawls on an NVIDIA chip?
Right. It's useless, practically. And that's exactly why they developed BDH GPU. It's the implementation, the way to run this theoretical forest model on our actual, silicon slabs.
How do they manage that translation? How do you get distributed graph logic into efficient tensor math without sort of breaking the underlying biological idea?
The key is how state is managed.
Yeah.
In a lot of LLMs, the connections to synapses or weights hold the long-term knowledge.
Yeah, the parameters.
In BDH GPU, they manage to localize the dynamic state into short vectors right at the neurons themselves. The computation still happens in this big, high-dimensional space using tensors for speed. But the logic, the way information flows and updates, stays true to that local, distributed, biologically plausible model. It lets them use the GPU's power without abandoning the core theory.
Okay, architecture makes sense. Distributed, local, biologically inspired, but GPU practical. Let's move to the mechanism, because this is where it gets, well, pretty provocative.
It really is.
Claiming your brain-like model actually explains the reasoning in a standard transformer. That's a big leap. What's the core claim about equivalence?
The central claim, and yeah, it's kind of shocking, is that the attention mechanisms we see everywhere in LLMs, they formally converge mathematically. They become equivalent to closed-form local graph dynamics at neurons and synapses.
Wow, closed form, so like a direct equation.
Basically, yes. They even call these the equations of reasoning. The idea is that all that complex, seemingly global attention stuff.
The dot products, the softmax, the big matrix multiplies.
It's actually mathematically the same as very simple, very local rules happening between spiking neurons.
Okay, I'm trying to wrap my head around that. Attention feels so global. It looks across the whole input sequence to see what's relevant. How does that boil down to just local interactions?
It simplifies reasoning, fundamentally, into two basic biologically plausible rules. Rules about how beliefs and connections get updated right there locally.
Right, give me rule one.
Rule one is basically inference. Think modus ponens. If you know A implies B, and you see A, you conclude B.
Logical implication.
Right, so if neuron I is active, it represents some belief or fact, and there's a connection strength, they call it sigma. I, saying I implies J. Then the activity at I boosts the belief state. The potential activity at J, it's just passing inferred knowledge along the connections in the graph.
Okay, that's propagating information. So rule two must be about learning or changing those connections.
Exactly. Rule two is Hebbian learning. The classic neurons that fire together, wire together. This is the plasticity part.
Ah, the brain's learning rule.
Precisely. If activity Y at neuron I is quickly followed by activity X at neuron J, then the connection between them, that sigma X, gets stronger. The significance of that implication is boosted.
So the network is literally rewiring itself on the fly based on correlations it sees.
On a very fast timescale, yes.
Yeah.
This is how the system updates its working knowledge, its context during inference.
Okay, wait. In a transformer, that short-term in-context memory is handled by the KV cache, right? This big temporary storage. Where does BDH store that?
This is the really neat part. There is no separate KV cache. The working memory, the context during inference, it's held entirely in the rapid changes of those synaptic strengths, the sigma matrix.
The fast weights.
Exactly. It's dynamic synaptic plasticity, driven by Hebbian learning with those spiky neurons. That is the working memory.
So the model's ability to, say, remember something from 100 tokens ago, that's physically encoded in how strong the connections between certain neurons have become right now.
That's the claim, and the evidence backs it up. The timescales involved for this plasticity, this potentiation, seem comparable to working memory timescales in the brain minutes, maybe, which map to context windows of up to hundreds of tokens in their tests.
So the big picture attention mechanism, like looking up things in the KV cache,
It corresponds directly, mathematically, to this local dynamic state stored on these synapses, these neuron-to-neuron links. Transformer attention is Hebbian plasticity in this framework.
That's quite a statement. A beautiful theory, but okay, does it actually work? Transformers are known for scaling incredibly well. Can BDH GPU actually compete?
Performance-wise, yes, absolutely. The empirical results show it follows transformer-like scaling laws.
Meaning add more parameters, get predictably better performance.
Exactly. On standard benchmarks, language modeling, translation, it basically rivals the GPT-2 architecture parameter for parameter from around 10 million up to a billion parameters.
That's impressive. GPT-2 is a solid baseline.
And there's a hint it might learn faster per token seen, which could be really useful if you don't have truly massive data sets.
Okay, let's talk scaling engineering. You mentioned it scales with N, the neuron count, and D, this low-rank dimension. How does that work?
It's potentially much simpler than scaling transformers, where often multiple dimensions grow together in complex ways. With BDH GPU, the main knob you turn is N, the number of neurons. That's the big dimension. It stays relatively small.
So N is huge, D is small.
Right, N is much, much bigger than D. And the total parameter count is basically just a constant times N times D. So engineers can focus mainly on scaling that one, biologically meaningful dimension, the size of the neuron population. It simplifies iteration and predicting how performance will improve.
That sounds elegant.
Yeah.
Very appealing from an engineering standpoint. What about the structure that emerges? If you just train this thing, does it organize itself in a brain-like way?
It really seems to. As it trains, the parameters naturally form a network structure that has high Neumann modularity.
Modularity, meaning it forms distinct clusters or communities.
Exactly. Clear functional modules emerge, often with a core periphery structure, very much like what we see in lots of complex systems, including, well, the brain. The network self-organizes.
Okay, so it forms these specialized groups. How does the architecture make sure, say, the language processing group doesn't get totally messed up by signals from the visual processing group, hypothetically? How does it keep signals within the right cluster?
That's where this mechanism they call ReLU low rank comes into play. You can think of it like an internal gating system.
Okay.
It's apparently very good at in-cluster Signal reinforcement. Basically, if a neuron gets a signal from within its own community, that signal gets amplified, reinforced locally.
But if it's noise from outside?
It tends to suppress it, so it acts like a local consensus mechanism, helps maintain that functional specialization within the modules, keeps things focused.
That self-organization plus the local rules, it really does sound like it's built for interpretability, doesn't it? If you understand the basics and it forms modules, maybe you can actually trace where knowledge lives.
That's a huge part of the motivation. Interpretability by design. And it goes beyond just looking at neuron activations. The activation vectors themselves are designed to be sparse and positive.
Sparse meaning most entries are 0.
Yeah, empirically, they find only about 5% of the activations are non-zero at any given moment.
5%. That's really sparse. What does that tell us?
Well, interestingly, that sparsity level seems correlated with how predictable the input is.
Oh, how so?
If the input is routine, expect it. Neuron activations drop towards 0. The network kind of ghosts, conserves energy. But if the input is surprising or novel or something needs to be actively remembered...
Activity spikes.
Exactly, activity spikes. It's like a built-in, resource-efficient, conditional computation. Only compute hard when you need to.
Fascinating.
Yeah.
But the real showstopper, the finding that really seems to nail BDH as this bridge, is the monosemantic synapses. Can you break that down? What does monosemantic mean here?
Monosemantic just means single meaning. And this is maybe the most compelling evidence. They showed that specific individual connection synapses reliably strengthen when the model processes or reasons about one particular concept.
Like one synapse, one idea.
Pretty much. They found, for instance, a specific synapse that consistently became more active, stronger when dealing with the concept of currency, and a different, distinct synapse for the concept of country.
And this isn't just word association, is it? The examples in the paper are key here.
Right, crucial point. It's about the abstract concept. That currency synapse, it strengthened for the English phrase British pound, but it also strengthened for the French phrase livre sterling.
So it's capturing the underlying meaning independent of the specific words or language.
Exactly. Even in relatively small models, under 100 million parameters, it's abstracting concepts and localizing that abstraction to a single, identifiable, measurable biological component, the synapse.
That is pretty incredible. And the engineering implications seem huge. If concepts are truly separated and live on specific connections.
It makes things like model merging suddenly seem feasible.
Right. If you have one model trained on, say, medicine and another on astrophysics.
Their knowledge should live in different sparse parts of this huge connection graph.
Yeah.
You could potentially just snap them together, combine to weight matrices. And because it's so sparse and high-dimensional, their knowledge bases might coexist without messing each other up too badly.
Avoiding catastrophic interference, the bane of model merging.
It could solve a massive headache for building more complex, specialized AI systems.
Okay, let's try to pull this all together. What's the big takeaway for us today? This Dragon Hatchling, BDH, it seems to provide that micro-level story for attention, the one von Neumann and Turing were searching for.
Yeah, it shows these biological ideas, synaptic plasticity, scale-free networks, Hebbian learning. They aren't just theoretical nice-to-haves. They can actually implement the kind of reasoning and language capabilities we see in state-of-the-art AI.
The biological approach works.
It works. And the flip side, the implication for neuroscience, is also profound. Well, maybe all the complex stuff we see in the brain, the modularity, the plasticity rules, the specific network structures, maybe they didn't just evolve over eons for general survival. Maybe they arose, more specifically, from the fundamental computational requirements of reasoning, of doing in-context inference efficiently.
Wow. So the brain's complexity might just be the optimal physical solution for implementing attention and logic.
It's a compelling thought, isn't it? That structure follows function, right down to the mechanics of reasoning.
And this whole line of thinking points towards what the sources call the ultimate goal. A new theory of thermodynamic limit behavior for these models.
Yeah, getting towards real mathematical guarantees. Like, probably approximately correct, pack-I-like downs, but for generalization over time, for reasoning.
Which shifts AI safety in a really interesting direction, towards axiomatic AI, building systems where we understand the local rules so well.
That we could actually make strong mathematical predictions about their future autonomous behavior, maybe even bound it.
So the provocative thought for you, the listener, is this. Why should you care about yet another AI model? Well, What if this model points the way to AI whose long-term safety and behavior could potentially be validated with just a few short, well-understood tests because we finally understand the fundamental axioms of its reasoning?
That's the promise here, moving from purely empirical AI to something with rigorous, predictable foundations.
An incredible prospect and a fascinating place for us to leave it for today.